In this video, we are going to find natural numbers x, y, and z such that xy plus yz plus zx minus xyz equals 2. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. I've come up with two approaches to this problem. The first one would be to recall that the expression on the left-hand side is actually part of a very beautiful expression, which is xyz minus xy minus yz minus zx plus x plus y plus z minus 1. So just taking either all three together, just taking 2 out of the 3, 1 out of 3, and not taking all of them, taking none of them at all, and multiply them together. So these are all the combinations. And for this expression, from what we are given, is actually equal to this part, the blue part, is actually minus 2. And then we add x plus y plus z minus 1. Then the wonderful thing is, the expression on the left-hand side can be factorized into x minus 1 times y minus 1 times z minus 1. And that is actually x plus y plus z minus 3. And it so happens that if I let a equals x minus 1, b equals y minus 1, and c equals z minus 1, then this equation becomes the product of a, b, c equals the sum of a, b, c. Now this is interesting because this becomes a much simpler equation, and we're solving for integers. This time, not natural numbers, but we only need them to be non-negative, because we know that from our condition, x, y, z is at least 1, and so consequently a, which is x minus 1, similar for b and c, only need to be at least 0, which means non-negative integers. So to solve this, we divide into cases. The first case is that at least one of a, b, or c equals 0. Then say, for example, a equals 0 by symmetry, or you can use the word w log. Then 0 equals b plus c, and you know that they are non-negative, which means b equals c equals 0. So that either or 0, then therefore x equals y equals z equals 1. So that's the first case. While for the second case is that none of a, b, c will be 0. Then I can divide both sides by a, b, c, and I have sum of 3 fractions, but all with numerator 1 and denominator some positive integer, is equal to 1. Again, it's a very common problem, adding 3 fractions together, which gives 1, and 3 of them are all proper fractions. So there is actually a bound on the largest fraction. Consider the largest fraction. So again, by symmetry, we can say that assume a is the largest, and so on. Then this is the largest fraction, because the bottom part is the smallest. So this fraction is at most, or as I say, at least 1/3. Because if it's even smaller, say it's 1/4, then the other two fractions cannot be larger than a quarter. So the sum would be at most 3/4, say 3/4, then it's even less than 1. So that's not possible. So it has to be at least 1/3. Either it's 1/3 or half. Of course, it can't be 1, because if it's 1, then the other two has to be 0, which is not possible. Then the other two is less than or equal to 1/3, and because it's the sum of these three fractions must be 1, so they must take the maximum case. Then, therefore, all the products must be 3. And so solving, like you can multiply and take square root, you realize that A, B, and C all have to be root 3. But that's absurd because we are looking for integers. So we can't have this case. If it's a half, then 1/AB plus 1/AC equals a half. Now we have two fractions that has to be a half, adding together. Then maybe I can just replace them by some less complicated alphabets. I should not cross it out. I should just solve it aside. Say if I have two fractions equals a half, then I can just add them up, cross multiply, move them to one side, and to make left-hand side factorizable, I'm going to add both sides by 4. Then I can factorize. And it turns out these two numbers can only be either 6/3, of course can be reversed, or both equal to 4. Then either, okay, it's the larger one, put it in front, it's either 6/3 or 4/4. Now I can solve if I should put this first. If it's 6/3/2, then if you solve it, you will get 3/2/1 for ABC. So xyz is 4/3/2 and its permutations. So here are some solutions. Well, for the last case, if it's a 4/4/2, then ABC you will get something like 2√2, 2√2. Sorry, not 2√2 for this. You will get √2 and √2 for B and C. But that's again absurd because we're looking for integers. So our only solutions are all 1 or the permutations of 4, 3, and 2. So we know the answer, and this is the first way for me to do it. Now it seems that this approach is quite complicated or quite tedious. Then my second approach would be to make use of the symmetry at the first place, which is to assume x is the largest. Then for the equation, I will write like this, and left hand side is actually less than or equal to (3xy), because I can say that this is less than or equal to x, this term, and this term is less than or equal to y. So we have 3xy on the left hand side. Then therefore, 3xy is greater than or equal to 2 plus xyz. Now from this, you can see that our smallest number, z, is either 1 or 2, because if z is at least 3, the number circled, then the expression at the right hand side must be greater than that at the left hand side, so that we can't allow this. So two cases. Case 1, z equals 1. Then you put it back into the equation. You have xy plus x plus y equals 2 plus xy. Then you can put away the xy, and all you have left is just x plus y equals 2. But you are solving for positive integers, so therefore both must be 1, and so you have triple ones again. And for case 2, z equals to 2, then xy plus 2x plus 2y equals 2 plus 2xy. So xy minus 2x minus 2y plus 2 equals 0. And you can do similar things, just like what we did in our first approach. You make the left-hand side factorizable, and then you do it. And because we have x larger than y, so I just take x minus 2 equals 2 and y minus 2 equals 1. And then solving, you will get x equals 4, y equals 3. So again, xyz is either triple 1 or 4, 3, 2, this set and its permutations. We only permute 4, 3, 2, but not the triple ones. Okay, so here are the two approaches that I have in solving this problem.